All right, here we go. 5.38 exponential functions in their graph. This should feel like a review because we spent an entire 3 weeks in Algebra 2 on exponentials.
That reminds me of the time. Man looks good right now.
Yeah. Anyways, so we're gonna go through this, and it feels like if it doesn't feel like a review, let me know, but hopefully it does. Okay. All right. So the first thing that we're gonna talk about is the definition that we have here, and the definition that we're gonna read is transcendental functions. Okay. What is a transcendental function, you ask? It's functions that are not algebraic. So up until this point, we've been working with algebraic functions. However, now we're working with functions that are not algebraic. Okay. Next thing we're going to also reiterate is the natural base E. One thing I've learned.
E is 2.17.
Almost 2.718. Okay. Natural base E. Turn it down a little bit. This is why your grade is what it is.
It's okay.
Yeah, focus. Focus. Natural base E. So it is E represents an irrational number. Can anyone tell me another number or symbol that represents a number? Pi. Okay. The value of E is approximately 2.718. Okay. That is the value of E. So when you see E, you treat it just like a number. It can be added, it can be subtracted, it can be multiplied, it can be divided, because it is a number, an irrational number, but a number nonetheless.
Why do you make the X look like
My equal? Because it's an approximation symbol.
Oh, I thought it was an X.
No, it's approximating. Okay. Now, the functions we did polynomials and rational in the last 2 units, right? We've had our polynomial unit and our rational function units. These are all examples of algebraic functions. Okay. Of algebraic functions. All right, now we're into exponentials and log. And the exponential, we're going to use function. We're going to use base A. So A is going to be our base. So our function that we're going to start with is f of x equals a to the x. Okay, we don't assign a value to A because A can be any positive number greater than 0, but not equal to 1. Okay. Okay, so just getting you in the habit of using your calculator to calculate expressions, because this is something you can put in the calculator. 5 to the 3/5. Can someone tell me also another way of writing 5 to the 3/5? Thinking back to Algebra 2, how else could this rational exponent could be written? Almost. Another way this could be written, the denominator represents your index of your root. Does that ring a bell? And the power, the numerator represents the power of the function. Okay. But yeah, so the denominator is the index of your root, the numerator is the power. Okay. But yeah, just wanted to bring that back up. But anyways, calculator. So inputting in the calculator. Just a refresher really quick on inputting in the calculator, you're just going to press 5. And you're going to use the caret button. I've been calling it a caret button since 8th grade. I think it's carry it, not carrot, like the vegetable. But oh well, here we go. You know what I mean? It looks like the tip of a carrot, right? That's what I'm saying. All right. So I hit enter and I get an approximate value. So my approximate value is, we're going to always practice rounding to the nearest thousandth unless said otherwise. So our approximate value is 2 and 627 thousandths. Any complications with plugging into the calculator? Hopefully not. Put batteries, put it on charger, be a problem solver. All right. Now, going to our parent function of the exponential. Okay, ignore the fact that your X and Y are drawn there. I thought, I didn't realize that after I printed the notes that your coordinate plane did not print along with it and it shifted down. So just ignore those, but you're supposed to have a coordinate plane drawn here. So if you don't mind drawing a coordinate plane of X and Y, and again, ignore what's already there.
We can draw a big in that there.
Yeah, you have that whole space. Just gonna pretend that you didn't see that.
Did we draw that guy?
Yes. Okay, so we're gonna start here. It says, for a greater than 1, is the graph f of x increasing or decreasing over its domain? So if a is greater than 1, is our graph increasing or decreasing? It is increasing because we read it from left to right. All right, for no matter what the exponential is, your exponential is going to always cross 0, 1. Okay, and it has a horizontal asymptote, so it has a boundary line at y equals 0 that's going to prevent you from crossing that. So exponential with a positive a, meant a greater than 1, is going to increase. Oh, I can't even pretend that I went through that. Couldn't even pretend. Try that again. Okay, you're just going to increase from left to right. So it's increasing. That's my a of x, okay? Now, what if it's a to a negative power? It's going to be decreasing. So if I have a to a negative power, it's going to be decreasing, but still, it's going to be going through 0, 1. Can someone tell me why both go through 0, 1?
Because it is.
Not because it's the origin.
Well, because it's power 0 is 1.
Exactly. Anything to the 0 power is going to be 1. Okay, so it's going to be now, I'm going to be decreasing.
Oh my God.
Okay, so here, when you're doing this, when you look at it, notice, remember, what does the negative in front of our x cause our function to do? Well, it causes our function to change it to be decreasing, but it causes our function to reflect over the y-axis. Okay, so because of this negative, before we even drew it, we should have known that it's going to be a reflection over the y. And did our values reflect over the y? Yes. Okay, talking back to our parent functions, what is the domain and range of our parent function? What's the domain?
0. Wait, no, I got him something to say. 0, yeah, no. 1?
The domain.
Oh, it's
Left to right.
negative. Negative infinity, yeah.
There we go. All real numbers. Negative infinity to positive infinity is our domain. Okay. Our range is what?
Oh, negative, no, 0 to infinity.
There we go. Our range is 0 to infinity. Okay. Our range is 0 to infinity. We get as close as we can to 0, and then we continue onward. Okay. The intercept, the y-intercept in this case, is going to always be what?
0.
0, 1 at 0, 1. Okay. And both have an asymptote at y equals 0. These are your parents, right? All the other functions are going to be modifications from it, right? This is the parent function, right? Everything is going to be a modification from it. So when I start adding more numbers to it, it's going to shift different ways, right? Okay. On your assignment, you have a problem, and on that problem, it says for you to graph, but I don't want you to really graph. I want you to tell me what's happening to the graph. Is it going up? Is it going down? Is it going left, right? Is it reflecting? How is it changing from the parent function of a to the x? Okay, that's what you're doing. All right, next, we're going to graph a function, and we're going to talk about graphing without a calculator. So graphing the sketch of the function, what you're going to be graphing is f of x equals 2 to the x, and we're going to have g of x equals 2 to the negative x. Okay, so we're graphing both of these. So we're going to start off with our first table, x, 2 to the x. And we just need to review some rules. We're going to be using -2, -1, 0, 1, and 2. If I have 2 to the -2, what does that equal?
1. Greater than 1 over 4.
What?
1 over 4.
That's just positive 1 over 4th, right?
Yeah.
Okay.
That.
You
So
said
negative 1 over, no, that's what, When I started for a while, but like recent. That's like when you put.
Yeah, okay. We're just gonna stop. All right, so when you have a negative exponent, that means you're gonna take the power, but it belongs in the denominator. Okay, so 2 squared is 4, but it's gonna go in the denominator, so it is 1 to the 4th power. Okay, but 1/4. So again, if you have x to a negative n, it's gonna become 1 over x to the positive n. Okay, all right, so next we have 2 to the negative 1. So 2 to the 1 power is 2, but because of the negative, it makes it 1/2. Good job. Anything to the 0 power?
Oh, it's always. That's what the negative does.
That's what the negative means.
So it's not like.
All right, and then 2 to the 1 is just 2, and 2 squared is 4. So this is the graph that we're graphing. So we're gonna do a little quick graph. So at 2, I'm at negative, getting there. I'm at 2, and I'm at 4. And again, we know that it has an asymptote. And there's my f of x. Okay, now we're gonna do g of x. Now, the difference between here is a negative. And we know based on our transformations, that negative is gonna cause what to happen? Is gonna cause it to reflect. And when I'm reflecting over the y-axis, what values are changing? Your x's. So instead of them being negative or positive, they're gonna change. But are my y values going to change? No, my y values are still going to be 1/4, 1/2, 1, 2, and 4. What's changing are my x. Instead of a -2, it's going to be a +2. Instead of a -1, it's going to be a +1. And we have 0, -1, and -2. So now at -2, I'm at 4. At -1, I'm at 2. 0 still at 1. At 1, I'm at 1/2. And at 2, I'm at 1/4. Okay, so I wanted you to see both at action. How if you find the positive power of the exponent, you can easily find the negative graphically. Are we comfortable with that? Okay.
Yes.
Yes, no, maybe so?
Yeah.
Okay, and so the negative again only changed the what?
X.
The x. Okay. All right, let's talk about the natural base e. So now we're going to dive into e a little more. And with our friend e, it is still an exponential function. It's just now the value of your a. So f of x equals e to the x power. Which is okay because e is a number greater than 1, right? That is very much true, right? Based on what we defined it as. So we're going to practice using the calculator to find this. So to get to e in your calculator, you're going to press second, and then you're going to press the ln button, the natural log button. Okay. So we're going to press second ln to get to our e. It's going to turn it on. I'm pressing second ln, and now I just type in 3/5. Okay. So I get approximately 1 in 822 thousandths. So e to the 3/5 is approximately 1 in 822 thousandths. Okay, how do you feel about inputting with e? Because again, it's just a number. Okay, it's an irrational number that we wrote on the first. We defined it in our at the top of our page, 2.718. Okay. Now notice if you hit second divide, you also get e, but you get e without a power. Okay. So if you hit second divide, you're gonna get e, but you're gonna get e without a power. So if I just wanted to know the value of e. Okay, got it? All right, let's continue. So next it says for the graph, we're going to use the calculator and graph e to the x. So we're going to graph e to the x in the calculator. Do you think it's going to be much different than 2 to the x?
No.
No, it is not. That's because exponential parent functions based on the a, they're just going to, the steepness of the curve is going to change, but not the value. Okay, so notice here I already have e to the x. So again, to get e to the x, I press second ln, and I put e to the x. Now I'm going to hit graph. And here's my function. Okay, it's growing a little faster than 2 to the x because of that 0.718, right? Other than that, it's the same thing. So what's the domain in range here? What's my domain? Negative infinity to positive infinity, because it goes forever to the left and forever to the right. And my range starts where? At 0. 0 to infinity and beyond. So we write our domain, negative infinity to positive infinity. Our range, 0 to infinity. And our intercept is still at 0, 1.
Wait, so will the range always be like to infinity? Because
Yeah,
Yeah,
not, it
it's
could be from negative infinity to a number if it's reflected the other way. Yeah.
But it's always infinity.
One of them. Yeah. All right, here we go. The number e can be approximated by the expression. So if you plan on going into calculus, this is one of the first limits you will define. Is the e, and I wrote it down because I wanted you to know it. All right, so this is one of your first limits you'll probably define. It's 1 plus 1 over x to the x power. And you'll talk about what is it approaching, what is its limit. And that limit that they achieved was a 2.718. That is the highest that number is going to go. It's going to have a lot of numbers that follow, but that is the highest that this value will end up reaching. Okay. All right, applications, real world example here. We're going to talk about interest. And so you have A is your account balance. You have T is your years, P is your principal, and your interest rate in decimal form, okay? When you're trying to find the compound interest, hopefully this sounds familiar, A equals P times 1 plus R divided by N to the NT, okay? Or compound interest, compound now uses the E. A equals P times E to the RT. Okay, and the key thing is, once you have the formula, you're going to read the problem and make sure you have all the information to solve it. Okay, so let's start with our A, compound interest. So on compound interest, you need to know your A, you're looking for your A. So your principal is 6,000. Your rate is 0.077%. If you're compounded monthly, how many months are in a year? 12. So your N equals 12. And for how many years are you doing this for? 10. So now I have everything I need to plug in, right? T.
Oh.
So now we plug everything in. So we have A equals 6,000 times 1 plus 700 divided by 12 to the 10 times 12. Okay. Once I have that, I just got to plug in the calculator, right? So I'm plugging in the calculator to figure out what is my A. How much, what's the amount I have earned? So in the calculator, I'm typing in 6,000 times 1 plus 700 divided by 12 to the 120. Okay, the key thing is setting up and inputting correctly. And you should have gotten $12,057.97. How you put it in matters. Okay, so we have 12,057.97. All right, on part B, you're now earning interest every hour, every minute, every second, every nanosecond of the day, right? It's compounded continuously. So when you're solving it, your A now equals, your principal is still 6,000, but it's E, your rate is still 7/10, and your time is 10. So now when you plug that in, you're gonna have 6,000 times second natural log of 7/100 times 10. And you earned, if it was compounded in continuously, you would earn $12,082.52.
Hey, this got some.
Okay, so that's the difference between the two. All right, that concludes it.